So far I've been talking about quadratic equations, and now I want to talk about a larger scope of the same type of equations. They're polynomials. So quadratic equations are polynomials. They're just polynomials with the highest term is the quadratic term here. But we can have polynomials with higher degree terms. So this would be our constant term, our linear term, quadratic term, our cubic term, our quadratic term, and our quartic term of the polynomial. And then I've done all this here to show that these polynomials can be nested. And actually this is another way to see what a polynomial is it's nested linear functions. It's linear functions that are nested inside of themselves. And the main point of this video is to show that this is a quicker way to evaluate a polynomial using this form here rather than using a form like that. So if I were writing a computer program, I wanted to evaluate a polynomial at, say, f at x is equal to 3. It really wouldn't be efficient at all to use this form, because then I would have to multiply 3 by itself 5 times and multiply it by 2 and then add it and do the same thing here, but with the degree being 4 and so on and so forth for each one of these terms. It would be a lot of steps to do that. And I might be able to do it faster by starting this way and then keeping a tally of what x is and just multiplying it each time, but that still wouldn't be very fast. The fastest way to evaluate this polynomial would be to evaluate this nested linear term first. So what I do is I would multiply 2 by 3 and then add 3 and then multiply by 3 and minus 1 multiplied by 3 plus 5, and we're keeping a running total as we go. Plus 5 multiplied by 3 minus 7 multiplied by 3 plus 1. That would be the quickest way to evaluate with the least number of operations, as opposed to doing calculating each one of those terms. And so what I mean by that is we could use this algorithm instead. So we write the coefficients in order. Here's 2, 3, -1, 5, -7, plus 1. So remember what we're doing with each one of these coefficient terms is we're multiplying it and then we're adding 1, and then I'm multiplying it by 3 and then I'm adding it. So I want to evaluate, I'll just erase that. I want to evaluate it at 3. So first I'm going to, let's see, drop the 2 down here, and then I'm going to multiply 2 by 3 and write it here. And then I'm going to add these terms up, and I have 9. And then I'm going to multiply the 9 by 3, and I get 27. Let's see if we're right. 2 times 3 is 6, plus 3 is 9, so 6 plus 3, 9. And then I take the 9 that's going to be here, and I multiply by 3, and I get 27. And then I subtract 1 from that, or I get 26. And then, so now, let's see, now this is 26, and I'm multiplying it by 3 again. So each time I move from here to here, I'm multiplying it by 3. So that's a times 3 times 3. So 26 times 3 to get to this term here is going to be 78. And I add 78 plus 5. In other words, 78 plus 5 is going to be 83. And then 83 times 3 is going to be 249. And then minus 7, or -7 plus 249, 242 times 3. I don't know where you get this huge number, but that's going to be 726. And so 727. Hopefully this math is right, because then it would kind of ruin my whole video. I think it's right though, but you guys can check my math and make sure it is. But basically what this algorithm just told me is that f of 3 is 727. And the whole point of this video is I just wanted to point out two things. Polynomials can be represented as nested linear functions. So this is a linear function nested inside of this linear function, nested inside this larger linear function, and so on and so forth. And I can represent all polynomials like that. And I also wanted to show that we can use this algorithm called synthetic substitution to evaluate these polynomials at certain numbers really quickly. And if we're ever writing a computer program, this would be the way to do it, rather than to brute force x to the 5th power, x to the 4th power, and so on.